Hi, today we're going to be talking about local maxes and local mins, absolute maxes and absolute mins, and how to find them. You should think about local versus absolute in terms of a mountain range. For example, in California, any mountaintop is going to be a local max. You climb up to the top, your highest point around. However, there's only one mountain in California that's the absolute highest. That would be Mount Whitney. So that would be the absolute max for all the mountains in California. And so in terms of where absolute maxes and absolute mins happen, the X value is where, and the Y value is the absolute max or absolute min. Sometimes you're asked for both. I typically will ask for both, but I'll always make it super clear what I want, so there'll be no confusion. All right, we need to talk about critical points before we can talk more about extrema. This is a definition that you do have to know. C is a critical number or critical point, same thing, of a function if two things happen. One, C has to be in the domain of F, and two, F prime of C is 0 or F prime of C does not exist. Now, why are those points interesting? Let's take a look at this picture over here. We want to approximate the derivative of f at a. Well, there's a horizontal tangent there, so f prime of a is 0. And then at c, there's a corner, so f prime of c does not exist. And you can see also there's a min at A and a max at C. So Fermat's theorem tells us that if you're looking for local maxes or local mins, then they're going to happen at a critical number. So that's why we're interested in critical numbers. All right, so before we get to the test for absolute max, absolute min on a closed interval, let's practice finding some critical numbers. Since critical numbers have to be in the domain of the function, you always have to know what the domain is. So in this case, the domain of this function is all x. E to the 2x has no problems, x has no problems, so the product has no problems. So now we want the derivative, f prime of x. We need the product rule, so we're going to have e to the 2x plus x times the derivative of e to the 2x. That would give us 2x e to the 2x. And we'll factor out an e to the 2x. We get 1 plus 2x here. So f prime of x equals 0 at x equals negative 1/2. Now the way I got that, let me move up here and show you my scrap paper. F prime of x equals 0 only if e to the 2x equals 0 or 1 plus 2x equals 0. So e to the 2x is never 0, and 1 plus 2x is 0 at x equals negative 1/2. So that's how I got that. And then f prime of x does not exist. That's the other place where you could have a critical number, and that happens never. So we've only got one critical number, and it's at negative 1/2. And you can see in my picture, there is a local min there, and in 2 sections, we'll learn a test that will tell us at a critical number, do we have a local max or a local min? But right now, we just need to practice finding critical numbers. All right, so for the next one, the domain of f, again, is all x. Now, we've got roots there, but they're both cube roots, not square roots or fourth roots. So cube roots we have no problem with. So f prime of x, I'm going to use this form of f in order to take my derivative. So we're going to get 5/3 x to the 2/3 plus 4/3 x to the negative 1/3. Now to find out where that 0 or where it doesn't exist would be almost impossible if we left it like it is. So we want to combine it into a single fraction without negative exponents. So first, let me write each of these as a fraction. This is 5x to the 2/3 over 3. And then this one, leave a space, is 4 over 3x to the 1/3. So our common denominator is 3x to the 1/3. So I need to multiply this guy by x to the 1/3 over x to the 1/3. And so what I'm going to get, my common denominator is 3x to the 1/3. And in the numerator, 5x to the 2/3 times x to the 1/3 is just 5x. Because when you add the exponents, you get 1. And then plus 4. So there's my simplified f prime. So f prime of x equals 0 only when the numerator is 0. So when a fraction is 0 only if the numerator is 0. 5x plus 4 equals 0, and that's x equal negative 4/5. And that's going to be one critical number because it's in the domain, and f prime of x does not exist when the denominator is 0, when 3x to the 1/3 equals 0, and that's at x equals 0. So we've got two critical numbers, and in this case, we do end up with interesting stuff happening at each of them. All right, so now we want to talk about absolute extrema. That just means maxes or mins. So if we have a closed interval, we have a theorem that tells us if as long as the function is continuous, there will be an absolute max and there will be an absolute min. So in this picture here, if I'm just looking at the interval from -1 to 2, absolute max is up here. That's, if I give both coordinates, that would be 0, 3, and the absolute min happens over here at an endpoint. That happens at 2, -5. All right, so let's learn a test. If we don't have a picture around, let's learn a test for finding out what those numbers are. And this is the test. It's super easy. Find the critical numbers in the open interval from A to B. A to B is the closed interval that you're given. Then make a list of f at the two endpoints and f at all the critical numbers. So evaluate f at those numbers and pick the largest, that's your absolute max. Pick the smallest, that's your absolute min. So we're going to do two examples. So for this problem, first we look for critical numbers. F prime of x is 2/3 x to the -1/3, and that's 2 over 3x to the 1/3. So f prime of x equals 0. That happens never. A fraction 0 when the numerator is 0. But f prime of x does not exist at x equals 0 because that's when the denominator is 0. So we have one critical number, x equals 0. So now we make a list. F of the two endpoints, -8, f of 1, and the order you put these in doesn't matter, and then f of the critical number, which is 0. So we evaluate f at those three numbers. So for the first one, f of -8, that's -8 to the 2/3. The cube root of -8 is -2. So that's -2 squared, and that's 4. F of 1 is just 1, and f of 0 is just 0. So those are easy. So we can see this is where we have our absolute max, and this is the absolute min. And so your homework will prompt you, absolute max value is, in this case, you would put 4, and that occurs when x is -8. I'll just have you give it as a coordinate pair. So for absolute max, you'll just write -8, 4, and for absolute min, 0, 0. Okay, let's do one more. And I've finished up the end of the problem for us just to save time, but I want to go through the derivative with you. So f prime of x is, you might want to pause the video actually and look for the critical numbers on your own. All right, I hope you did that. 4x cubed minus 16x, and that's it. And let's factor that. That's 4x. That's what we can pull out. And what's left is x squared minus 4. And we can factor that even more. That's x plus 2, x minus 2. So f prime of x equals 0 at x equals 0, x equals -2, and x equals 2. Those are all critical numbers. However, this guy is not in the interval from -1 to 3. So we don't have to worry about that. So we just have to worry about these two critical numbers and the two endpoints, -1 and 3. Now I went ahead and evaluated f at those four numbers. You can see I made a list. 25 is the biggest number. That's the absolute max. So that happens at 3, 25. And 0 is the absolute min, and that happens when x is 2, 2, 0. And you can see that that's the case with this picture here. All right, and that is the end of this section.